Hi, Ronan.
Hi, Eugene. Hi, Forough.
Hello. Okay, so let's get started. So it's my distinct pleasure to introduce today's speaker, Forough Arabshahi, currently at Carnegie Mellon University, working with Tom Michel on a very exciting new direction of research that aims to learn by natural language based interactions between computers and humans. And before then, she did a PhD at UC Irvine, working with Anima Anakuma and Samir Singh. And what I really like about Forough's research is that she's focusing on the very difficult and challenging reasoning problems by combining a wide range of techniques, including neural programming, deep learning, and probabilistic graphical models. And today, she's going to tell us about all of those during her PhD as well as postdoc at CMU. So one more thing, just a sec. So I forgot to mention that per usual, we are going to hold our questions until the end, unless if you have clarification questions, maybe you can leave a question on the chat box, but otherwise we'll wait until the end. Thank you. Go ahead.
Thank you, Yajin. Thanks for the nice introduction. And thanks for giving me the opportunity to present my research today here. So today I want to talk about neuro-symbolic learning algorithms, which are hybrid models that combine two major directions in artificial intelligence research, which is that of neural networks and symbolic reasoning, and show you different applications of these learning algorithms for problems in reasoning. So reasoning refers to our ability of making sense of the world around us. For example, our common sense tells us that the ground gets wet if it rains. And humans have impressive mathematical reasoning, logical reasoning, and common sense reasoning abilities. Humans can think hierarchically and recursively about problems. And they approach problem solving by breaking problems down into smaller subproblems that are easier to solve. And it is this hierarchical and recursive thinking strategies that are believed by many to be one of the major contributors to the formation of thought and language in humans. Computer scientists have long had the dream of making machines that can automatically learn and reason, removing the need to manually program them. So let's see how far away we are from that goal today. I have chosen an example from the Winograd Schema Challenge. So consider this sentence. And the trophy doesn't fit in the brown suitcase because it's too small, versus the trophy doesn't fit in the brown suitcase because it's too large. So notice how strikingly easy it is for us humans to understand what it refers to in these two sentences. This is because we possess common sense. But computers can still solve this challenge. And despite the efforts of AI researchers since the 1950s, common sense and automated reasoning remains to be an unsolved challenge at the heart of AI. And my overarching research goal is to develop efficient learning algorithms that address the problem of reasoning and common sense reasoning. So towards that goal, I have developed models that can be categorized under three broad umbrellas of probabilistic models, deep learning models, and neuro-symbolic algorithms. On the probabilistic front, I have developed latent tree graphical models that can be used to model high-dimensional time series data, such as predicting behavior of students in a massive open online course, or behavior of social network attendees like Twitter or Facebook. Also, I have developed latent variable models that for which we can prove interesting statistical learning guarantees applicable to topic models. And on the deep learning front, I have developed tree-structured neural networks applicable to the problem of mathematical reasoning, mathematical question answering, and verification. And I have further augmented these recursive neural networks with external memory to improve their extrapolation capability to extrapolate to harder mathematical reasoning problems. On the neuro-symbolic front, I have developed a lookup and adapt semantic parser that combines natural language spoken statements into logical forms understandable by the computer. And I have also developed a hierarchical neural theorem prover for the problem of common sense reasoning. And this can be categorized more under general artificial intelligence. And today, I want to talk about these three models in this talk. So let me start by telling you about the challenges that we are faced with when addressing the problem of reasoning. The first challenge is that of extrapolation. So often in reasoning, the computer encounters problems that are much harder than what it has seen before, say during training. So it's important for its underlying learning algorithms to extrapolate to these harder instances of the problem. And in my PhD, I focused on developing different probabilistic and deep learning algorithms that address this challenge by extracting hierarchical structures from data that helps break down problems into smaller subproblems that are easier to solve. The second challenge is that of explainability. So often statistical learning algorithms are not explainable, so that it's not easy for us humans to understand why they are making certain decisions or certain errors. And it's important for them to be explainable because we want to understand if the decisions and errors that these models are making are driven by common sense and reasoning abilities, or are they due to artifacts in the data. And in my research, I focus on developing explainable algorithms. The third challenge is that of instructability. So even if we are given an explainable machine learning algorithm such that we can easily understand why they are making certain decisions or errors, how can we easily fix the errors that they are making? According to the current big data statistical learning paradigm, we need to collect more samples and retrain the underlying algorithms. But this is very inefficient. Wouldn't it be great if we could just directly teach computers in natural language the way we teach our fellow humans? My research focuses on developing instructable algorithms in which humans can directly teach computers in natural language. So this talk is about neuro-symbolic algorithms. So let me give you a very brief history about these models. Connectionist models or neural networks were introduced as early as the 1930s. And the term artificial intelligence itself was introduced in a conference co-organized by Claude Shannon, John McCarthy, and a few other colleagues in 1956. After that, in 1963, Newell and Simon proposed symbolic manipulation as a plausible model of the mind. And in the 60s and 70s, the major approach to artificial intelligence research was that of a symbolic approach. And it was around 1970s the connectionist method lost popularity, mainly due to a negative result proved by Minsky. And it was around 1980s that connectionist methods started regaining popularity. And as they were getting more and more popular, Forough began a debate dismissing connectionist models as a plausible model of the mind, arguing that they lack systematic generalization abilities. And I'm going to tell you in a little bit what the systematic generalization is about. Fast forward to today, in 2010s, neural networks are being used to model, to solve numerous problems, but still the systematicity challenge remains. And it was around 2014 that researchers started regaining attention to neuro-symbolic algorithms that combine these two major directions in AI research. So let's see what this symbolic versus connectionist view is all about. In the symbolic space, if we represent knowledge in terms of interpretable facts and rules that are typically encoded in logic, and we perform logical inference to make inferences about that knowledge. And because these systems are represented in terms of facts and rules, they are highly explainable because we can easily understand the rules by looking at them, and they provide systematic generalization. So let me tell you what this means with an example. In the symbolic space, if we learn the meaning of an unknown word like clap, we can easily clap twice and jump and clap. So we can easily compose learned symbols with already known symbols to find and to form new ones. But the problem with symbolic models is that they lack generalization and knowledge coverage. For example, it's such that it's not always clear how we can represent the entire world knowledge in terms of facts and rules. For example, how can we represent a cheetah in terms of facts and rules? It's not clear. And it was this lack of knowledge coverage that set symbolic models aside for a few decades. On the other hand, connectionist models that are learned using many examples provide very good knowledge coverage. For example, we show a neural network many examples of a cheetah, and it can easily categorize or classify an unseen cheetah for us. So neuro-symbolic models combine these two views to overcome the limitations of each. And specific to the neuro-symbolic models that I develop is the capability of extrapolating to harder reasoning problems, and also defeating data sparsity, because often connectionist methods are very data hungry. And I focus on developing efficient learning algorithms. So let's see why neuro-symbolic models allow us to achieve overcome the limitations of these views. It all comes down to the local versus distributed representation views. So in the symbolic space, representations are local. Let's say I have a domain in which I have two fruits, apple and orange, and two people, Bob and Alice. If I want to represent this knowledge in a symbolic language, this is how I would define it. And the way I would store this symbolic knowledge in the computer is to store it locally. So let's say I want to store apple. One thing I can do is to store it in a single location in the memory. You can think of it as a one-hot vector, where I have a 1 for symbol apple and 0 everywhere else. And we can do the same for orange by storing it in another location. And if we go about representing symbols this way, what happens is that from the perspective of the computer, we can replace these symbols with random symbols A, B, C, and D, and nothing changes. Basically, this local representation lost the meaning of the original symbol, and all of these representations are orthogonal to one another. Whereas neuro-symbolic models allow us to learn distributed representations, such that we distribute this representation for, say, the symbol apple across all the entries of a vector. And because we distribute this representation, we need a smaller vector to represent the symbols in the vocabulary. And the point about this distributed representation is, let's say I project this down to the 2D space just to view it. If we learn good representation, then what's going to happen is that, say, apple and orange will be bundled together, and Alice and Bob will be bundled together, such that semantic similarity in the symbol space translates to vector similarity in the vector space. And this is what neuro-symbolic models allow us to achieve. So in this talk, I want to introduce two of our two applications of the neuro-symbolic algorithms. The first one being in mathematical reasoning, and the second one in logical reasoning for the problem of common sense. So let me start by mathematical reasoning. And in this part of the talk, I focus on the problem of extrapolation and talk about how, by extracting hierarchical structures from data, we can achieve extrapolation. Okay? So hierarchical structures appear in many different domains. For example, in natural language, sentences can be represented in terms of their hierarchical syntax tree that has a hierarchical structure. Symbolic expressions also have a hierarchical structure by using their syntax tree. For example, this expression sine squared theta plus cosine squared theta equals 1 has this hierarchical structure that comes for free with this equation. Another example is this numeric expression, 1 plus 2 times 3 equals 7. And in this part, I focus on a problem called neural programming, where we use neural network for modeling different functions, be it from the mathematics domain, for example, power, sine, cosine, or from the logic domain, like and or even from the computer programming domain, like this implementation of the addition function. And the goal of mathematical reasoning is to learn distributed representations for different functions like sine and cosine, and different symbols like theta and numbers like 2.45. And the point about these representations is that expression similarity would map to vector similarity in the vector space, as you can see in this figure on the right-hand side. So you might ask, why should we even bother learn these distributed representations for functions in mathematics? Can't we use symbolic solvers like Mathematica and Symbi, and don't they already solve this? So the short answer is no, but I'm going to give you a perspective of why it's good to perform research in this direction. Back in the 20th century, Shannon set 4 goals for artificial intelligence researchers to achieve by the year 2001. The first goal was to develop a computer program that beats a chess champion. The second was to develop a computer program that proves the elusive Riemann hypothesis. The third was to develop a computer program that beats the prime rate stock prediction by 50%. And the last was a computer program that writes a novel that gets accepted by the New Yorker. And ever since then, we've had good progress towards the first and the third goals. And very recently, by the advent of language models, towards the fourth goal, but not much towards the second goal. And this performing research in this direction addresses this problem. And because this is already a challenging task for the current machine learning algorithms, performing research in this direction provides a test bed for further progressing machine learning research. And we will also see that we can improve the performance of a symbolic solver because these symbolic solvers are often implemented using search heuristics, and it can take them forever to solve complicated mathematical problems. Moreover, we will see an added benefit of these. We can use machine learning for scientific discovery by solving differential equations. So the applications I want to talk about today are first for mathematical question answering. We're given a mathematical expression. The goal is to find a value for the blank that satisfies this equation. The second application is that of mathematical equation verification. We're given a math equation. We want to verify if it's correct or incorrect. And the last is solving differential equations. So let me start by showing you the types of training examples that we use for our model. The first type is that of symbolic expressions. These are expressions that contain symbols and, of course, numbers. But the point about them is that they encode relationships between the functions in our mathematics domain. The second type is data of function evaluation expressions. These are evaluations of different functions in the domain. For example, a sine of minus 2.5 is minus 0.6. We can have evaluations for addition, say 2 plus 2 equals 4, and so on. And the last one is representation of floating point numbers. We represent floating point numbers by their decimal expansion tree. For example, 2.5 is 2 times 10 to the power of 0 plus 5 times 10 to the power of negative 1. And the reason why we choose this representation is that all floating point numbers can be represented with integers 0 through 10. And if we only learn good representations for these 11 integers, we can generalize to an unseen floating point numbers. This is a method called data augmentation, where we use data from different sources. And prior to this, researchers in neural programming either used only symbolic expressions or function evaluations, be it from the mathematics domain or the computer program domain. And we will show that this is important for achieving extrapolation. Our baseline is a chain-structured model. And so this is a recurrent neural network that has a feedback loop onto itself. And I have chosen a long short-term memory or an LSTM architecture. And the way it works is that I'm going to unroll this in time. I will walk over the sequence from left to right and input this sequence to the recurrent neural network and pass this all the way through. And at the very end, I predict whether this equation is correct or incorrect. But remember that these expressions came for free with their parse tree. So the model that we propose is a tree-structured model. And the way it works is that we are going to assign different neural network blocks for modeling different functions in the domain. For example, we have a neural network for the function sine, a neural network for the function cosine, and so on. And what we are going to do is we are going to compose these neural networks such that they mirror the structure of the input equation. And these blocks that I have chosen are long short-term memory or LSTM blocks. So this structure is called a tree LSTM. And the way I would input this expression to this architecture is through the leaves. So I input the symbols and numbers through the leaves and pass this equation all the way up until I get to equality. And at equality, what we do is we look at the vector representations in each subtree of equality. And if the input equation is correct, we minimize the distance between these two vectors. And if it was incorrect, we maximize the distance of these two vectors. And this is how we learn the distributed representations for expressions. So remember, we also had function evaluation and number encoding expressions. In order to model these, we introduced two new neural network blocks, the number encoder and the number decoder blocks. And again, we compose all the neural network blocks to mirror the input structure and input the equation through the leaves or terminals and walk all the way up until we get to equality. And at equality, what we do is we use the number decoder block to decode the representation back to a number, and then minimize the mean squared error between the right-hand side and the left-hand side. And this is jointly trained with the previous one, so we optimize both of these losses jointly. And in order to evaluate these, we have generated a data set containing these mathematical expressions. And this is because this is a controlled generation, we can generate a balanced data set containing correct and incorrect mathematical identities. And we also had about 1,000 function evaluation expressions in the data. So let me start by the first application, which was mathematical question answering. And here, given this equation, I want to predict a value for this blank. The way we do this prediction is to use the blocks that were trained previously. And what we are going to do is we are going to generate random candidate predictions from the vocabulary for this blank. And then we are going to plug in these candidates into this expression and use the previous model to rank these candidates at equality to see which one is correct. And we get the output probability of the model as a ranking metric and rank these predictions. If the correct prediction is at the top prediction, we are going to count that as a success. And here I want to show you the performance of the chain-structured model, LSTM, compared with the tree-structured model. And you can see that only by accounting for hierarchical structures in the data, we can get 60% performance improvement. But this is a very hard task. So let's make it a little easier and see if we can help the chain-structured model. We are going to look at the top K predictions of the model. And as long as the correct prediction is among these top K, we are going to count that as a success. So here, I show the accuracy of the model as I increase K from 1 to 10. So 1 is just the value of the table that I just showed. And even though this accuracy increases for the chain-structured model, there's still this large gap here that is that is achieved only by accounting for hierarchical structures in the data. So now let's move on to the next application, which is that of equation verification. We're given an input equation. We want to verify if it's correct or incorrect. So this is basically evaluating the two-class classification task that we trained the models for. And the first evaluation I perform is that of generalization. So I want to see how well the model generalizes to an unseen expression. So one note here is that, remember, these expressions had a parse tree associated with them. I'm going to take the depth of the parse tree as a metric for how complex these expressions are. And in the first evaluation, I want to see how well the model generalizes to an unseen expression of the same complexity. So what I do is I split my train and test data such that I have equations of depth 1 through 4 in the train and depth 1 through 4 in the test data. Here I show you the accuracy of the two-class classification, and I compare the model against a symbolic solver called SymPy, and the chain structured model and the tree structured model. And you can see that the chain structured model and the chain structured and the symbolic solver are performing similarly, whereas we can gain about a 15% performance improvement just by accounting for hierarchical structures in the data. Okay, so in the second evaluation, I want to see how well the model extrapolates to a harder mathematical problem. So what I do is I keep equations of depth 1 through 3 in my train and test the model on equations of depth 4, which are longer and deeper expressions, so potentially harder. And I'm going to show you the performance side by side with the previous evaluation. And you can see that the performance of the symbolic solver and the chain structured model drops drastically, whereas the performance of the tree structured model drops only by 1%. And this shows the effect of hierarchical structures allowing us to achieve extrapolation. So I was interested in seeing what the limit of this extrapolation is. So what I did was I generated more data and kept training data of kept data of equation of depth 1 through 7 in train, and tested the model on equations of depth 8 through 13. And interestingly, the performance of the tree structured model starts to decay drastically as I move away from the depth of the training data. So this is showing depth from 8 through 13, right? So the reason why this is happening is that, first of all, the representations that we learned for the functions were not perfect. And because these equations get deep, error propagates worse and worse up the tree. So in order to solve this, what we propose is to increase the memory capacity of each LSTM cell using a stack. The LSTM cell itself is trained to push and pop to that stack. And the intuition for using that using a stack comes from the difference between the recursive and iterative counterparts of an algorithm. So often the recursive implementations of algorithms are much shorter. For example, this iterative implementation of the multiplication function requires us to do 2 for loops over the digits of the numbers that are being multiplied, whereas the recursive implementation only has a recursive call onto itself. So and we know that recursive algorithms are implemented and executed using a stack. So by giving the model access to a stack, we are encouraging it to go for the recursive implementation, which is shorter and easier to model. And then hopefully we can learn better representations. So this is the structure of the tree LSTM compared to the structure of the stack augmented version. And the reason why this structure allows us to defeat error propagation is that in the tree LSTM architecture, each node only has access to its direct children, whereas in the stack augmented version, each node also could have access to the states of its grandchildren by popping items from the stack, because the grandchildren also push to the stack of the children. And this is how we defeat error propagation. So let's see the performance of this stack augmented neural network for the data set that we just saw earlier. We can see that the accuracy remains quite flat using this stack augmented neural network. And we can see that this allows us to achieve extrapolation to harder mathematical problems. The other application of this model is in modeling ordinary differential equations. So the goal here is to find the f of x that satisfies this expression given ai's and b. We have really good preliminary results showing the applicability of the model in modeling ODEs. Differential equations are used to model numerous phenomena in real world. I won't have the time to show all the results here, but I would be more than happy to discuss these offline if you're interested. So to summarize, in mathematical reasoning, we saw how we can learn distributed representations for different functions and symbols in the mathematics domain. And we saw how we can achieve extrapolation by extracting hierarchical structures from data and also further augmenting neural network with external memory. So far, I talked about hierarchical structures that are observed in the data. But what if we have hierarchies that are unobserved? In that case, we can use probabilistic graphical model to learn the hierarchical structures in the data. Moreover, sometimes even hierarchical models are better at modeling different problems, for example, in topic models. And in both of these cases, we can use probabilistic graphical models and latent variable models to extract these hierarchical structures that allow us to achieve better performance. So far, we saw the problem of extrapolation, how we can achieve extrapolation by extracting hierarchical structures. In this part, I want to switch to the problem of explainability and also instructability. And we are going to switch gears here a little bit and show our common sense reasoning engine and see how we apply neuro-symbolic algorithms for logical reasoning. And in this part of the talk, I want you to imagine yourselves as you are talking to your phone assistant or home assistant like Alexa or Siri. And now imagine you're talking to your assistant and you tell your assistant, if it snows at night, wake me up early. So if your goal was to account for traffic slowdowns caused by snow in your commute to work, what you probably meant was if it snows enough to cause traffic slowdowns and it's a working day, then wake me up 30 minutes early. So it turns out that humans often underspecify these intents because humans have common sense, and they also assume that other humans have common sense and can easily uncover these underspecified intents. The question that I would like to answer is, can computers also uncover these underspecified intents or not? So let's go back to our previous example. If it snows at night, then wake me up early. And now assume you also indicate the reason why you want to achieve this to your personal assistant. For example, you can say, because I don't want to be late to work, or you can say, because I have never seen snow before. So notice the striking difference between these two because goals and how easily we can understand them. In the first scenario, you probably don't want to wake up on a weekend if you don't work on a weekend, whereas in the second scenario, you do, no matter what day of the week it is. My goal in this work is to see if the computer can also use these because statements to uncover the underspecified intents that we humans can easily uncover. And to formally define the problem, we are given a statement in the format of if state S, then perform action A because I want to achieve goal G. And the goal is to extract these underspecified intent. So to make them more clear, let me walk you through an example for the previous sentences that we just saw. In the first scenario, the underspecified intent is that we need to indicate how much it should snow for us to wake the user up early. And we also need to indicate what days of the week does the user work. Whereas in the second scenario, we need to figure out somehow that we need to wake the user up before snow melts and that the day of the week doesn't matter. And we should wake the user up no matter what day it is. The solution we propose for this is to perform multi-hop reasoning. So let's go back to our to work on time example. And in order to indicate what I mean by multi-hop reasoning, I want to show you the reasoning chain for this particular statement. So I'm just going to read this multi-hop chain of reasoning out loud to you. If it snows more than 2 inches, then there will be traffic If there's traffic, then my commute time to work increases. If my commute time to work increases and I leave the house earlier, I will get to work on time, and I will leave the house earlier if I wake up earlier. So this is what I mean by a multi-hop chain of reasoning. And the reason why I want to, and from now on, I will refer to this as a proof for the input user's goal. So this is a proof for getting to work on time. Okay, and the reason why I want to extract this chain of reasoning is that the user's underspecified intents will appear in the proof trace if you're able to extract it. So for example, here, the user didn't mention anything about the amount of precipitation, but it pops out in the proof trace. So I want us to take a closer look at this proof trace. First of all, notice that it contains if S then A statements. So these are similar to statements in atomic. And also notice that if I unroll this reasoning chain, it's actually a tree rather than a chain because I have an and or a conjunction in one of the logical statements. And therefore, this results in a proof tree rather than a proof chain. And also notice that these dashed lines here rely on exact match between the if statement of one logical rule and the then statement of the preceding rule. This is going to be challenging, and I'm going to talk about it in a little bit. So let's sneak peek into our solution. The first step is to convert if-then natural language statements to statements in logic. For example, if I wake up earlier, then I will leave the house earlier becomes, so this representation goes from right to left, it's a little weird, wake I early, then leave I house early. And once we have these representations in logic, so these are basically just converting if S then A to S then A statements in logic. And then we are going to use a logic programming language to program a background knowledge called KT, containing these if-then logical statements, okay? And then we get the user's if S then A because G statement and submit the goal to this knowledge base, submit it as a query, and perform logical inference to extract this proof tree, which is a reasoning chain that we are looking for. And the way this reasoning chain is, or proof tree is extracted is that in each step of proof extraction, we look at the input query. Here, the input query is G, and then we get a relevant entry from the knowledge base whose left-hand side starts with G. And then we look at the leaves and go and traverse the leaves one by one. Here, we need to find a match for A, which is the second entry, and a match for C, which is the fourth entry here. And this goes all the way until we finish the proof. And you can see that the user's underspecified intent pops out here. So the user only stated S, A, and G, and this is the user's underspecified intent that we want to extract. Okay? So let me talk about the challenges that this logical inference poses when dealing with natural language statements. The first challenge is that, remember, these if-then statements are from natural language. And since people have different ways of referring to the same thing, this will result in drastically different logical form representations for semantically similar statements. For example, one user can say, if the weather is snowy tomorrow, whereas another person can say, if the forecast calls for snow tomorrow. And these will result in different logic forms and would prevent us from doing this exact match that this proof extraction requires. The second challenge is that we can't assume we can represent the entire world knowledge in this small KT background knowledge. So KT is bound to be incomplete. So how can we address these? In order to address these challenges, in order to address the first challenge, which is duplicate entries of K, what we do is we learn distributed representations for these statements in logic. And the added benefit of this is that this provides us explainability because these representations have rules associated with them that we can easily interpret. Moreover, in order to deal with the incompleteness of K, we engage in a conversation with the user and extract that knowledge just in time from the user. So let's see how we can learn these distributed representations of logic. We are given a background knowledge KT for which we want to learn distributed representation. So we will have a distributed representation for each entry in that background knowledge. And our training data is a set of proof traces that are submitted as queries to this background knowledge. And the model has an LSTM controller at its heart that chooses the relevant entry from the background knowledge as we walk down the proof trace. So the way, and it also tells us when to terminate. And the way it works is that in each step of the proof, we maximize the probability of choosing the correct next rule as we traverse the tree. So the model is a hierarchical model that walks down the proof trace and picks the correct next rule, and also tells us when to terminate each branch. And this is how we will learn these distributed representations. So let me give you the overall overview of the common sense reasoning engine. We are given statements in the form, if state S, then perform action A because I want to achieve goal G. And then we parse these statements into their logical form representations. And then what we do is we take the user's goal as a query, and we submit it against our background knowledge. We do a search, and if the goal is not in the background knowledge, we engage in a conversation with the user that extracts the goal from the user just in time. And if the goal was in the knowledge base, then great. We are going to, in the next step, use our learn distributed representations to extract proof traces, in which we can have the user's underspecified intents. All right. So what we did was we went ahead and ran a user study in which we collected these if, then, because statements from users. And one interesting thing we noticed when collecting these statements was that about 85% of the users gave statements that follow the above format, which is achieving an actual goal, whereas the other 15% provided more of a condition metadata rather than an actual goal. For example, one user said, if the price for plane tickets home gets below $1,500, then buy it because it is a good price. Because it is a good price is not an actual goal, so we're going to ignore these 15% statements and just focus on the first 85%. And then what we did was we ran these common sense reasoning engine using actual users. And here I want to show you sample dialogues from the study. Let me start with a successful instance. The input statement was, if it's going to rain in the afternoon, then remind me to bring an umbrella because I want to remain dry. And the reasoning engine asked, how do I know if I remain dry? And the user said, if I have my umbrella. The reasoning engine asked, how do I know if I have my umbrella? And the user said, if you remind me to bring an umbrella. And here reasoning succeeds, and the engine says, okay, I'll remind you to bring an umbrella. Now let's see a failed instance for the same utterance for a different user. So again, the system asked, how do I know if I remain dry? And the user said, if I have my umbrella. The system asked, how do I know if I have my umbrella? And the user said, if it's in my office. The system asks, how do I know if it's in my office? And this conversation just goes on without being able to get an actual proof. So this is our overall results from that study. We had two types of users. Novice users were users that have never interacted with the system before, and expert users who were well familiar with the functionalities of the model. And the numbers in this table show the percentage of the statements that were successfully proved in a user interaction setting. The no feedback scenario is a model that engages in no conversation with the user. And if we don't engage in a conversation, we're not able to solve any of the reasoning tasks. And I just want to note that we can't really use, even a random baseline wouldn't be able to achieve more than 0% because this is a challenging task. Soft prover is the performance of our learned distributed representations that we just saw. For our soft prover, novice users were able to prove 18% of the statements, and expert users were able to prove 33% of them. And oracle prover is a prover that has access to perfect distributed representations such that they succeed whenever they should and fail whenever they should. And for this Oracle prover, our novice users achieved proved 26% of the statements, and our expert users' performance improved to 48%. So this was nice because it showed us that we can indeed rely on human users to give us explanations with which we can complete these proofs. But notice that there's still a large gap to perfect performance. And this is the reason why we have been collaborating with Yejin's group at AI2 and incorporating her COMET model into our prover. And we have very interesting results where we have showed that this number can drastically improve. And we have also shown that using Yejin's COMET model, we can drastically reduce the user interaction. And which is one of the reasons why I'm very excited about this position particularly. So let me summarize our common sense reasoning engine. We saw how we can learn distributed representations for different statements in logic, and how we are able to extract users' underspecified intents by extracting proof traces. We saw that this allows us to achieve explainability because these these distributed representations have a corresponding logic rule that can be easily interpreted. And we saw how by engaging in conversation, we can achieve efficiency for scenarios where we have little data available. So in conclusion, we saw how we can achieve extrapolation by extracting hierarchical structures, and how we can gain explainability and instructability. In the future, I'm interested in a few interesting directions, and I'm going to start with my short-term plan. I'm interested in developing self-diagnosable learning algorithms. So as we know, most data-driven algorithms are not explainable. And so far, I only have done research on discriminative neuro-symbolic algorithms. In the future, I'm interested in developing generative neuro-symbolic models that generate symbolic outputs, that can be used as explanations of the model's decisions or errors. And my aspiration for this one is that users should be easily fix the errors that the model is making solely by explaining to the model through conversation. In the longer term, I'm very excited about the possibility of instructability. So notice that recently, due to the advent of conversational agents like Siri, or a home assistant like Alexa, we have been able to talk to our computers. And the AI research community is currently in the early stages of understanding how to take advantage of this added new conversational capability. But I believe that the time is right to leverage this interaction to enable conversational learning. Conversational learning is a new learning paradigm in which humans can directly instruct computers in natural language to achieve new tasks. And the point is that today, if we want to add a new functionality to our computing devices, we should go and learn the computer program, the computer's programming language. And currently only 1% of the human population can do that. But if this type of conversational learning succeeds, we would suddenly find ourselves in a world where 99% of the end users can add new functionalities and capabilities to their phones just by conversing with them. And another view of conversational learning is that it can be viewed as a complement to the current big data statistical learning that dominates the field of machine learning right now. And I'm interested in seeing how natural language explanations can allow us to achieve more sample efficient algorithms and improve the accuracy of current statistical machine learning models. And because in these type of conversational learning, we are interacting with users, there is always possibility of acquiring incorrect knowledge. So it's important for these models to be able to detect and self-detect its wrong beliefs and output them so that users can directly fix them. Moreover, humans often rely on making clarification dialogues to combat natural language ambiguity. I'm interested in seeing how these clarification dialogues with computers can also allow them to overcome that. And of course, central to all of these problems is the problem of semantic parsing. And I'm interested in performing research in this direction. I would like to thank my co-authors and the funding agencies that made this research possible. And thank you so much for listening. And I'm ready to take questions.
Okay, so that was a great talk, and maybe we can give her a round of applause if you could unmute.
Thank you. Thank you so much.
Questions?
Can you hear me?
Yes.
I'm going to start just to give other people a chance to think of more insightful questions. But you know, the vision you described there towards the end is very compelling. One of the big challenges, whenever I've thought in that direction in the past, has been around evaluation. Right, when you get people in the loop and the sort of ideas, it seems very challenging to evaluate unless we go to kind of extensive user studies and things like that. And of course, our community evaluation centric. So I wonder what your thoughts are about how to address this issue.
Yeah, I do agree with you that evaluation is a big issue here, and this is actually what we have been struggling with. And it's also hard to convince people to trust these user studies. So I do agree with you that this is a challenging thing right now for this research direction. And I don't know how we can address it, but other than running user studies for now.
Thank you.
Any other questions? I will ask one question. So I think it was about slide 56, maybe, where you were showing the performances from the user study on your conversation. So none of these are using Comet, if I understand right?
Yes, I haven't shown Comet results here.
What happens with that? I mean, you said that it was helped, but...
Yes, so it helps us to close this gap and make it closer to 100%. I don't have the numbers here, but another a very important effect that Comet had was that it helped us reduce user interaction. So we don't need to go as much to the user anymore. So you can think of this as maybe the no feedback scenario performance also improves, I guess.
And that was using the off-the-shelf Comet, not even the newer version that we actually started developing after talking to you guys.
Okay.
So it should work even better. But so that's just minor detail. But I have a little bit more philosophical question about the especially the second half of the talk, where you had this conversion of natural language into logical forms. And so the question is this critical? Does it actually help the performance, or might it work better without it? And the inverse of that question is, do you think Comet could work even better if you injected some sort of a logical forms in the middle?
So that's a great question. Yes, we are currently converting these to logic so that we can perform multi-hop inference. I did see your work on dynamic QAs that also performed multi-hop inference using Comet, and that was very interesting. But I have a question here that I can ask you later. But it wasn't clear to me how we can directly use Comet to do multi-hop inference just off the shelf. And the other question you asked was, sorry, can you say again what your other question was?
Oh, so like basically, I'm questioning how much how important is it to have logical form conversion from natural language description? So in your case, you do have that version, but you don't have the other possibility where logical form conversion does not happen, and yet still do some sort of neural reasoning just across natural language descriptions. And if it turns out to be important for you, it might be important for Comet too, or might be helpful for Comet too. So
So I think, so the short answer is that I'm not sure how you can do multi-hop reasoning the way a logic inference engine allows you to achieve if you do not convert these to logic. And we have very recently started actually converting comments if then statement into logic statements to see how this works. But this requires us to scale up our reasoning engine, because currently we are working with very small background knowledge. And in order to scale it up to the entire comment domain, that's an interesting thing that we are currently working on. And I think the benefit of using logic or converting this to logic is the possibility of using the possibility of achieving multi-hop inference. And it's my understanding that if you just do it the way you do in the dynamic QA, I could be wrong, but the search space grows exponentially. So I'm not sure how you guys handle that.
So
maybe
we don't need to, because of the fact that we just generate these things in the way that neural network generates language. And when neural network generate language, we do not consider exponentially many different possibilities. So there's that, but I can see that in your case, you do face that because of what logic programming does require. You gotta like specify everything out. So
right,
you see that the scalability will be a challenge due to that.
Yes.
Yeah.
Mm-hmm. Yep. Thanks.
Any other questions?
Hey, I have an open question with respect to to treat the numbers or symbols as well and natural text simultaneously. I think these days some NLP people are interested in reading text with numbers, and they are struggling with it because it is really difficult to understand the numbers and text, I mean words and phrases at the same time, because natural text includes like units, like 3 kilometers and 3 meters are totally different, but symbolically it only contains 3. So as I said, this is a kind of open question, but I'm thinking that your first part of the talk is dealing with symbolic mathematical manipulations, and I'm wondering how I can borrow that idea to solve those kind of natural text understanding with symbolic numbers expressions.
Right. So if you can give, like, if you can extract the symbolic expression that is being specified in that natural language expression, then you can later apply this tree structured model. But off the shelf, you need a structure to be able to apply these models directly. So unless extract an expression tree out of that natural language statement, which I can see the number of ways that can fail, you cannot use this, I guess.
Okay, yeah, thank you very much.
Yeah, sure.
I think we have time for one more question. No? Okay, so let's thank the speaker again.
Nice talk.
Thank you so much. Thanks for listening.
So Forough, I think you have a break now for about 15 minutes, and then we can meet at 11:15.
Okay, thank you so much. See you soon then.
Awesome talk. Talk to you soon. Bye-bye.
Yeah, talk to you. Bye.